Okay, let's unpack this. This deep dive, it's focused on a really critical new development in non-autoregressive language modeling. We're looking at this paper, Loopholing Discrete Diffusion, Deterministic Bypass of the Sampling Wall. So we're jumping into discrete diffusion models, DDMs. Now, you probably know they're super promising alternatives to the standard autoregressive models, AR models, mainly because of parallel decoding. Yeah, generating the whole sequence at once. That's a huge speed advantage. But the big issue, the elephant in the room, has always been quality. They just haven't quite matched AR models there. This paper, though, it's from researchers at KAIST, EPFL, and Microsoft. They don't just put a Band-Aid on it. They pinpoint and actually fix a fundamental flaw that seems to be causing that quality gap. All right, so here's the quick rundown for you. The main problem, something the authors call the sampling wall. It's this major information collapse. Think about it. The model internally has this rich picture, right? A full probability distribution over possible next tokens with all the confidence scores. But the second it samples a token for the next step, poof, it collapses down to just a single one-hot vector, like this token, and that's it. All the nuance about how sure it was or what other options were close, gone. And that lost information, it can't be passed along, which leads to problems like the model getting stuck, repeating steps, or just oscillating wildly.
Exactly. And the fix they propose is honestly pretty elegant. It's called loopholing. What it does is introduce a second pathway, a direct deterministic path that carries this, let's call it, rich contextual state around the sampling bottleneck. So you still have the normal stochastic path, the sample token, but you also have this continuous latent pathway, preserving all that internal context, the model's confidence across the denoising steps.
And the impact is, well, it's pretty significant. These loop-pulling discrete diffusion models, LDDMs, they make huge strides in quality. We're talking generative perplexity, gen PPL, slashed by up to 61% compared to the old baselines. That's massive. And get this. One version, LDDMU, which uses a uniform diffusion approach, it actually beats the quality of their AR baseline after about 500 sampling scats.
Yeah, it really closes that gap. So our mission today is basically to break down how this deterministic bypass actually works. What are the nuts and bolts? We need to get into the computational trade-offs too. Is there a cost? And really understand why holding on to this latent information is so crucial for these iterative models. It's all about injecting that memory back in.
Okay, let's set the stage first. The problem itself. Before loopholing, we had these two main types of DDMs, right?
You had mass diffusion models, MDMs like MDLM, using that MS token prior, and then uniform diffusion models, UDMs like UDLM, using a uniform prior. Their big plus was always parallel generation, leveraging global context.
Right, but the problem happens at that reverse diffusion step when it actually has to pick a token. That's the sampling wall you mentioned.
Precisely. That's the moment of collapse. The model internally generates this, let's call it a high-fidelity prediction vector. It's got probabilities for every single token in the vocabulary. Super rich, continuous information. But then for the next step of the diffusion process, that whole rich vector gets squashed down into one single discrete thing, the sampled one-hot token.
And the paper has this brilliant example. It really makes it click. They imagine predicting between just two tokens. Okay, case A, the model's output vector is maybe like 0.49, 0.51. It's basically guessing, super uncertain. Case B, the vector is 0.20, 0.80. Now it's pretty confident about the second token.
Right. Now, let's say in both scenarios, the random sampling process happens to pick the second token. The output passed to the next step is the exact same one-hot vector in both cases. The next denoising step has absolutely no way to know whether that token came from a confident prediction or a near-random guess. All that valuable info about certainty, about alternatives, just gone, thrown away.
Wow, okay. So every single step, this sampling wall is potentially discarding crucial context. It's like the model figures out the answer is B, and it's 80% sure, but all the next step sees is B, with no idea about that 80%. And without that context carrying over, the next step is kind of flying blind, having to refigure things out.
Exactly right. It forces recalculation. And the authors link this directly to two really obvious failure modes you can see when you watch these models run. First is what they call steps without progress, or idle steps. Because the input sequence isn't really changing meaningfully, that context was lost, the model might just output the exact same prediction for several steps in a row. It's just spinning its wheels. Total waste of computation.
Okay, idle steps. That makes sense. What's the second one?
Excessive oscillation. This happens if the model, by chance, samples a low probability token. Say it was really confident about quiet, but happened to sample loud. Because that context, that memory of preferring quiet, is lost due to the sampling wall, the model doesn't easily correct itself. Instead, this error can destabilize the whole process. It forces the model to keep repredicting, jumping back and forth, oscillating, instead of smoothly refining the sequence.
Right, it can't make those small conservative adjustments because it lost the memory of what it was trying to do. Okay, so the sampling wall is the villain, loopholing is the hero. How does the fix actually work architecturally?
So in a standard DDM, the network computes its internal state. Let's call it the dollar state, this rich representation. But only the simple sample token actually makes it to the next step, tall on color. Loopholing changes what comes out of that denoising step. It still produces the stochastic sample token, the one hot vector, whatever, but it also explicitly outputs and passes forward that deterministic continuous latent vector, DETO-DAL. Think of DETO-DAL as the model's internal confidence register. It holds that high-dimensional context that was previously being discarded.
Okay, so it's producing two things now, the token and this hidden context.
Yeah.
How does it actually smuggle that context into the next step's calculation? How's it integrated?
It's like building a parallel memory bridge. In the old way, only the single sampled token crosses the gap between time steps. Loopholing adds this second hidden pathway for the context HSizzle. Specifically, it takes the latent context HSizzles from the previous step and it fuses it, combines it, with the embedding of the current sampled token CLSILs. They use layer normalization in there, probably to keep the signal scales manageable. This combined representation then becomes part of the input for the next prediction. So the network gets to see not just the token chosen, but also the rich context that led to that choice, allowing it to maintain a sort of continuous internal state.
Okay, I see. But wait, doesn't that create a huge training problem? Now, the output of step tech directly feeds into step plus plus. That sounds like a recurrent dependency. Normally, that means you'd need back propagation through time, unrolling the whole sequence, which is super slow, and exactly what diffusion models try to avoid.
You absolutely hit the nail on the head. That's the potential trap. Training it like a standard RNN would kill the efficiency gains. But they have a really clever workaround. Self-conditioning. It's a technique to simulate that context propagation during training without needing to backpropagate through the entire time sequence. It essentially teaches the model to use its own generated context.
Okay, simulate it. How does that work in practice during training?
It's a two-pass approach for each training example, each noisy input. Pass 1. They run the loopholing denoising function, but they initialize the incoming context state AT to 0. This generates the sort of first draft of the context. Let's call it HE. Pass 2. Now they run the denoising function again on the same noisy input, but this time they feed in that tier from pass 1 as the context. And here's the crucial part. They apply a stop gradient operator, SG, to that $10 out.
Ah, the stop gradient. So that cuts off the gradient flow backwards from pass 2 into pass 1.
Exactly.
It means the gradients for the final prediction only depend on the current step's computation, keeping training fast. But the model does see its own previously generated context over dollars as input in pass 2.
Right. So it forces the model to learn how to use that context effectively, how to condition on its own internal memory state, without the computational cost of propagating gradients back through time. It's like teaching it to read its own notes from the previous step.
Clever. And they mix this in. It's not done for every single step.
Yeah. The final training loss is a mix. With some probability PD, they calculate the loss using this self-conditioned output from pass 2. The rest of the time, probability 1 ppm, they use the standard DDM loss without the self-conditioning. They found that a relatively high probability PO, somewhere between 0.5 and 0.9, worked best. So the model gets a lot of practice using its own context.
Okay, well, that's a neat trick to sidestep the recurrence training issue. But okay, the big question. Proof is in the pudding. Did this fancy architecture actually lead to better text? Let's get to the results.
Oh yeah, the results are pretty striking. Let's talk language modeling first. On open web text, just looking at validation perplexity, the baseline MDLM got around 23.05. The loopholing version, LDDMM, brought that down to 21.90. But generative perplexity, GenPPL, which really measures fluency and coherence of the generated text, that's where you see the massive gains. LDDMM cut GenPPL by 55% compared to the baseline MDLM, and LDDMU, the uniform version, cut it by a huge 61% relative to its baseline UDLM.
61% reduction. That's enormous. It almost sounds too good. Is it consistent, though?
That's perhaps the most compelling part. If you look at how perplexity changes as you increase the number of sampling steps, the baseline models, they tend to plateau pretty quickly. They make some progress, but then they kind of get stuck. They stop improving much. LDDMs, however, show this consistent downward trend in perplexity all the way out to 2048 steps in their experiments.
So that confirms the deterministic pathway is actually working. It's letting the model continuously refine the output step after step, avoiding those idle steps we talked about.
Exactly. It's enabling meaningful iterative refinement, and that's how they challenge the AR models. Remember that LDDMU variant? It didn't just get close to the AR baseline's Gen PPL, which was 34.40. It actually surpassed it after 512 steps. By 124 steps, LDMU was down at 28.76 Gen PPL.
Okay, beating the AR baseline on quality while keeping the parallel generation speed. That's kind of the holy grail for non-autoregressive models, isn't it?
Pretty much. It shows that the core DDM idea with this architectural fix is genuinely competitive on quality.
And it's not just about perplexity schools, right? They also looked at how human-like the output felt.
They did. They used the G-Evil framework, which involves getting ratings from GPT 4.1 on different quality aspects, and LDDMM scored significantly better than the baseline MDLM on things like consistency. It went from about 3.2 up to 4.3 on their scale, and naturalness jumped from 2.4 to 3.6.
So GPT-4 thinks the output is more coherent and sounds more natural. That ties back directly to preserving that context, right?
It seems highly likely. Richer context allows for more consistent and natural-sounding generation. And the ablation studies really drill down into why it works. They measured something called temporal KL divergence, or TKL. Think of TKL as measuring how much the model changes its mind between steps. High TKL means big changes. Low TKL means smaller, more stable changes.
Okay, so what did TKL show?
In the early steps, what they call the exploration phase, LDDMs actually showed higher TKL. They were making faster progress, changing things more aggressively than the baselines.
Getting to a good rough draft faster.
Sort of. But then in the later steps, the exploitation phase, the trend flipped. LDDMs showed lower TKL than the baselines. This suggests that once LDDM has built up a good contextual understanding via the deterministic path, it becomes more stable. It makes smaller, more conservative refinements, avoiding that wild oscillation we discussed earlier.
Less thrashing around once it finds a good path. Okay. And what about prediction confidence?
They looked at token prediction entropy, TPE. Lower entropy means higher confidence. The model is more certain about its predictions. And LDDMs consistently maintain lower TPE throughout the denoising process. That stable context path seems to allow the model to be more decisive, more confident in its predictions at each step, because it's not constantly losing and trying to rediscover the context.
Makes sense. Stable memory leads to more confident decisions.
And critically, this isn't just about making text sound fluent. The benefits carried over to complex reasoning tasks. They tested on arithmetic reasoning benchmarks like Countdown and the Game of 24. These require holding intermediate steps in mind, exploring possibilities.
And loopholing helped there too.
Significantly. For example, their 85 million parameter LDDMG model hit 63% accuracy on Gaming 24. The baseline MGDM, only 47%.
Wow, a 16-point accuracy jump just from adding that memory pathway.
Yeah, it suggests that preserving that rich state helps the model explore the solution space more effectively, preventing it from getting locked into a wrong path too early just because of a single poorly sampled token. It's about maintaining the complexity of the thought process.
That is a really powerful finding. It's not just surface-level fluency, it's impacting deeper reasoning capabilities.
Okay, so summing this up, loopholing looks like a genuinely fundamental improvement for discrete diffusion models. It tackles that core sampling wall limitation, enables proper iterative refinement, and pushes the quality much, much closer to AR models, even surpassing them in some cases. But everything has a cost. But what's the trade-off here? Did they sacrifice the speed advantage?
That's the crucial practical question. There is a trade-off, yes. Training time increases by about 30%. And memory consumption goes up a bit too, because you're essentially carrying around this extra deterministic context, embedding alongside the standard token embeddings. So training is heavier.
30% more training time.
Yeah.
Okay, but what about inference, the actual generation speed? That's the good news. Inference time is largely unaffected. Because it's still a parallel decoding process, adding that extra context pathway doesn't significantly slow down how fast it generates the final output.
Okay, so you pay more upfront during training to build a better model, but it still runs fast when you need it to generate text. That seems like a reasonable trade-off for many applications.
Exactly. Especially if you need high throughput or real-time generation, that inference speed is key and the quality boost is substantial.
Listening to this, the idea of passing a hidden state forward, it really echoes recurrent neural networks, RNNs.
It does have that flavor, definitely, passing state information across time steps. But the brilliance of the self-conditioning is that they get that RNN-like memory capability without the RNN training nightmare. No slow backpropagation through time. They keep the simulation-free, efficient training that makes diffusion models attractive.
They got the memory benefits without the sequential training penalty. That's quite an achievement. Okay, so this brings us to that final provocative thought you mentioned, the one the authors raised. They tried applying the same loopholing idea, this deterministic context path, to a standard autoregressive model.
Right. And what happened, basically?
Yeah.
Not much. They saw maybe a tiny improvement in perplexity, but no real meaningful improvement in the actual quality of the generated samples.
So this mechanism that dramatically fixes and boosts iterative, non-autoregressive models has almost no effect on a standard sequential autoregressive one.
Exactly. Which leads to a really interesting question for you to think about. Why? Why does adding this explicit memory path fundamentally change the game for DDMs, solving their core issues, but barely register for AR models? What does that tell us about the fundamental differences in how these two types of models generate sequences, and perhaps more importantly, how they fail? Something to definitely mull over regarding the future of parallel text generation.